Okay, so this is I'm solving with everything together. I mean, we will use the location of the gravity center and also the reaction force, so the equation of equilibrium. So we need to add that it's a steel plate with a density equal to, thickness equal to 0.3 meter and density it's equal to 7,850 kilogram per meter cube. Okay, so to find the weight, we will need to use the area times the thickness times the density and times g to find the weight. But first, let's find the location of the center of gravity. So we need to find x bar, that's equal to the integral of x tilde dA divided by the integral of dA, and y bar, that is equal to the integral of y tilde dA divided by the integral of dA. Okay, so we have the two equations. We have the equation of the top, that is this one, and the equation of the bottom, that is this one. Oops, I highlight them because we will need them all the time. Here we go. Okay, so for our little element of integrations, I will use some vertical stripe. Okay, so that's my dA, okay, in blue, and my dA is equal to what? So on the x-axis is dx. Okay, so this is dx, and on the y-axis, this length is y. It's y2. So this one, let's call that y2, and let's call this one in green y1. Okay, and y2 was in red. Here we go. So this is y2 minus y1. Can you see? So my dA will be y2 minus y1 and time dx. So that the height of the rectangle is the limits between y2 and y1. So what is y2? dA is equal to, so y squared equal to x, so y it's equal to the square root of 2x. So it's equal to square root of 2x, and minus y1 is minus x, so minus x dx. So we can just rewrite it dA it's equal to the square root of 2x plus x dx. So that's for the dA. Okay. So we wrote dA in terms of x only. So now we need to write x tilde and y tilde in terms of x. So the center of the rectangle is somewhere there. Okay. So that's for this is x tilde, and this is y tilde, right? So we have for x tilde, it's equal to just x. And for y tilde, it's equal to the middle of this rectangle, the middle of the length. The middle of right is y1 plus y2 divided by 2. That's the way we find the coordinate of the middle of a line. So y tilde it's equal to y1, that this one, minus x, plus y2, that the square root of 2x, and divide by 2. Oops. So let me rewrite it one more time. So that's equal to 1/2 of square root of 2x minus x for tilde. So now we can find the location of the gravity center because we have everything in terms of x. So let's find dA. So the integral of dA it's equal to the integral of the square root of 2, oops, what's that? the integral of dA. Let me write it there. I think I need more space. The integral of dA is equal to the integral of square root of 2x plus x dx. And x is going from, so that's x from 0 to 2. So from 0 to 2. And you know what? Let's plug that in the calculator. Let's open the calculator for you. Here we go. So we enter math number 9 from 0 to 2. And this is, oops, the square root of 2x. That was minus 2 or plus 2? Let me plus for the x here. That was a plus x dx. Enter. So 4.666. So there it's equal to 4.67 meter square. That's for the dA. Now on the top, the integral of x tilde dA, it's equal to the integral of, so x tilde is x time square root of 2x plus x dx from 0 to 2. So let's enter that in the calculator. Oops, let's come back on the calculator. Okay, so math number 9 from 0 to 2. And we have x parentheses, the square root of 2x plus 2 plus x, sorry, plus x. Close the parentheses, dx. 5.867. So it's equal to 5.867. And it means that we can find x bar. If we use this and this, we have x bar that is equal to 5.867 divided by 4.67. And that's x bar is equal to 1.257 meter. And now let's do y tilde dA. It's equal to the integral from 0 to 2 of 1/2 of square root of 2x minus x. So that's the y tilde time the dA, that is the square root of 2x plus x dx. We can simplify this because there is some a minus b plus a plus b. That's a square minus. Let's simplify it before we plug that in the calculator. So y tilde dA is equal to 1/2 of the integral from 0 to 2 of 2x minus x squared dx. So let's use this in the calculator. Let me write it on a piece of paper so I don't forget it. 1/2 of from 0 to 2 of 2x minus x squared dx. Here we go. So the calculator there. So 0.5, don't forget 0.5 time second, not second, just math number 9 from 0 to 2 of 2x minus x squared dx. 0.6667. So this is equal to 0.667. So we use dA and y tilde. and we get y bar that is equal to 0.667 divided by 4.67, and y bar it's equal to 0.143 meter. So we have x bar and we have y bar. Here we go. So now what we do with that? We come back on our plate. Okay, so we have the plate like this. And now we know the location. So that's 0, 0. That's x. And that's y. And we know that C is somewhere there. And this distance is 1.257, and this distance is 0.143. Okay, and let's look at now at the force. So what we know the weight, and we know that the weight is at C. So that's the weight. How much is the weight? The weight is equal to the density. No, first. So the weight equal to m. Let me do one step at a time. M times g. It's equal to the mass. It's equal to rho times v. So times g. It's equal to rho times v. It's equal to v. It's equal to the area times the thickness times g. Okay, so it means that your W it's equal to rho 7850 times the area, that is where the area, this one, 4.67 times the thickness, that is 0.3, times g, that is equal to 9.81. So how much is that? Do I have it there? Let me check. It's equal to 107.8 kilonewton. So that's your weight. Here we go. Now, for the force that we don't know, we have a normal force at B, which is supposed to be red. Normal force at B that I will call NB. And I know that the angle is 45 degrees because that's 2 and 2. And we have two reaction force, AX and AY. And we need some distance, so we know that this one is 45. We know that this distance, that's your, let me put it in, that's the X bar, that is equal to 1.257. And we need this distance, that is 2 meters, and this distance, that is 2 meters. Here we go. We don't need the how we call that, Y bar. So now we can solve for NB using the sum of the forces. I completely changed my scale that I use for writing, but let's go on the left. I have this now. Let's solve for sum of the moment about A. It's equal to 0. So we have, in the negative direction, we have minus W times 1.257 and plus we have, oh, you know what? We don't have to, instead of using 2 and 2 and the complement, let's use the perpendicular distance, that is this one, and the distance D. So it's plus NB times this distance and this distance D, that the hypotenuse of a little triangle that is 2, 2. So that's 2 square roots of 2. So when we have a square that is 2, this one is 2 square roots of 2. You can do it, can prove it by D is equal to 2 square plus 2 square, like this. So it's equal to 4 plus 4. So it's equal to square roots of 8, and square roots of 8 is 2 square roots of 2. So NB times 2 square roots of 2 is equal to 0. So we find, and the W, so we find NB that is equal to the W, that was 107.8 times 10, 3 times 1.257 divided by 2 square roots of 2. And we find NB in kilonewton, 47.9 kilonewton. That's a lot because the plate is very, very, very heavy. For some of the force on, let's do X first. Some of the force on X, it's equal to 0. We have AX plus NB cosine 45. It's equal to 0, and NB is 47.9. So we find that AX is equal to minus, so it's in the other direction, 33.9. And one last steps. We will do sum of the forces on Y, it's equal to 0. So on Y we have AY minus W and plus NB sine 45 equals 0. So we have AY that is equal to 107.8 minus NB, so 47.9 sine 45 degrees. And that's, hello, I try to move, but I can't. Oops, here we go. So AY, it's going up and it's 73.9 kilonewton. AX, AY. Oh, here we go. So we cannot find the reaction at A and B before we find the location of the center of gravity, because we know we need the location of the gravity center to find the moment about A due to the weight. So that's why we have done all those steps. So that was a long one. And we are done. We are done with this chapter. I see you in the next chapter. This chapter is easier because we will use usual shape to find the center of gravity. This one is one of the most challenging chapters. Okay, bye-bye. See you.